Hartnell governor is the spring-loaded governor. It consists of two bell crank levers pivoted at point OO to the frame. The frame is attached to this spindle so that it can rotate with it. Now, a spring in compression provides the equal amount of force on this roller. Each lever carries the ball at its vertical end and a roller at its horizontal ends. Whatever the force comes on this roller through this collar on the sleeve comes. So it can be adjusted with the help of this nut provided on the top of this spindle by screwing up and down. Let M is the mass of each ball in kilogram. Capital M is the mass of sleeve in the kilogram. R1 and R2 are nothing but the minimum and maximum radius of rotations, R1 and this one R2. Omega 1 and omega 2 is the angular velocity at minimum and maximum radius of rotation in radian per second. S1 and S2 are the spring force exerted on the sleeve at omega 1 and omega 2 in Newton. Fc1 and Fc2 are nothing but the centrifugal force at omega 1 and omega 2. S is nothing but the stiffness of the spring or the force required to displace the spring by 1 mm. X is the length of the vertical arm. Y is the length of horizontal sleeve arm. R is nothing but the radius of rotation. Now, for the further analysis, consider the single bell crank lever and what are the forces shown here for the maximum and minimum position. So, let H be the compression of the spring when the radius changes from R1 to R2. For minimum position, when the radius changes from this R to R1, the sleeve lift H1 is given by this geometry and this one. So H1 divided by Y equals to A1 divided by this distance, that is X. So A1 is nothing but R minus R1 divided by X. We can get the relation number 1. Similarly, for maximum position, when the radius of rotation changes from this R to R2, the sleeve lift H2 is given by this geometry and this geometry. So H2 divided by this Y equals to A2 divided by this distance X. So A2 is nothing but R2 minus R divided by X will remains as it is. You can get the relation number 2. Now add equation 1 with equation number 2. You can get H1 plus H2 divided by Y towards the left side, and towards the right side here R minus R1 plus R2 minus R divided by X will remains as it is. So this R get cancelled and we can get this relation H1 plus H2 divided by Y equals to R2 minus R1 divided by X, or we know this H1 plus H2 is nothing but H. So H divided by Y equals to R2 minus R1 divided by X. Since here H is nothing but, already discussed here, H is nothing but H1 plus H2. So in the next step we can get H equals to R2 minus R1 into Y divided by X. You can get the relation number 3. Now for further analysis, for the minimum position, for this minimum position, taking the moment of all the forces about this point O and equating the same. So first force with us here, mg plus s1 divided by 2 turns about this point in clockwise direction. This one mg also turns about this point in clockwise direction. This one turns about this point in anti-clockwise direction. So by considering the rotation direction, you can write this relation mg plus s1 by 2 multiplied by this distance y1 equals to fc1 multiplied by this distance minus mg multiplied by this distance. So by doing the further simplification, we can get mg plus s1 equals to 2 by y1 into this term which comes as it is. Again, for the maximum position, taking moment of all the forces about this O point and equating the same for equilibrium of this ball. So we can get mg plus s2 divided by 2. So first force is here, mg plus s2 divided by 2 multiplied by the distance y2 equals to fc2 turns about this point in anti-clockwise direction. So fc2 multiplied by this distance plus mg multiplied by this distance with us a2. So you can get this relation mg plus s2 equals to 2 divided by y2 into this term. Now subtract the equation number 4 from this equation number 5 so that we can get the difference between the spring force. That is mg plus s2 minus mg minus s2. So mg get cancelled. We can get s2 minus s1 towards the left side, and towards the right side this term minus this term. We know difference between the spring force is nothing but s2 minus s1 equals to h into s, and this relation from equation number 3, h equals to r2 minus r1 into y by x. So you can get from this relation s equals to s2 minus s1 divided by h goes in denominator. So replace the h by this term, that is r2 minus r1 multiplied by x divided by y. Now neglecting the obliquity effect of the arms, that is x1 equals to x2 equals to x, and y1 equals to y2 equals to y, and the moment due to the weight of the ball, that is due because of this mg. We have for the minimum position mg plus s1 by 2 multiplied by y equals to fc1 multiplied by s, or you can get mg plus s1 equals to fc1 multiplied by x by y will come here. Similarly, for the maximum position mg plus s2 divided by 2 is the central force with us. We have to take the moment of the central force about this O point. So mg plus s2 by 2, this distance with us, by neglecting this obliquity effect, we can just say y2 is nothing but the y. So mg plus s2 by 2 multiplied by y equals to fc2 multiplied by x. So you can get this relation mg plus s2 equals to 2 into fc2 multiplied by x divided by y will come here. So next equation with us here. Now in this case, the subtracting equation number 6 from equation number 7, we can get s2 minus s1 equals to 2 into fc2 minus fc1 into x divided by y. If you look towards the right side of both the equation, we can get this relation. Now we know that s2 minus s1 is nothing but h into s, and h equals to r2 minus r1 into y divided by x. Simply replace this h term here with this term. Okay, h2 minus s1 divided by h equals to 2 into fc2 minus fc1 divided by this one r2 minus r1 into x divided by y whole bracket square will come here. Okay, this is nothing but the equation number next. Okay, now here unless and otherwise the effect of obliquity is mentioned and the moment due to weight of the ball is mentioned, that is neglected here. When the frictional force is taken into account, the weight of the sleeve is replaced by mg plus minus f. Then next one, the centrifugal force at any position, that is intermediate position, by considering the minimum and maximum positions. Okay, for the minimum and intermediate position, you can write S equals to 2 into Fc minus Fc1 divided by R minus R1 into X divided by whole bracket square. Okay, give equation number next for this one. Now for the intermediate position and for the maximum position, we can get this relation 2 into Fc2 minus Fc divided by R2 minus R into X divided by Y whole bracket square. Now from equation number 9, 10 and 11, the left side is same, so you can equate the right sides. So you can get this relation Fc2 minus Fc1 divided by R2 minus R1 equals to Fc minus Fc1 divided by R minus R1 equals to Fc2 minus Fc divided by R2 minus R. So equating this term with this one and this term with this one, we can get this relation, that is Fc equals to Fc1 plus Fc2 minus Fc1 into this term, and by equating this term with this one, you can get Fc equals to Fc2 minus Fc1 into this bracket, that is R2 minus R divided by R2 minus R1.